Hi everyone, my name is Pooja, and today I'm going to be sharing our research, physiological and neurophysiological measures used to quantify cognitive workload of UAS operators. Safety critical tasks demand complete precision. Errors can have serious consequences. When mistakes do happen, they're often due to two main factors: poor training or increased cognitive workload. Cognitive workload refers to the mental effort required to complete a task, and it varies based on the task complexity and a person's abilities. Accurately measuring this workload is essential, not just to understand errors, but to improve training and optimize performance in high stakes environments. Traditional methods, like the NASA Task Load Index or the NASA TLX survey, are simple to use but can be subjective and intrusive to administer. Behavioral metrics are often another option, but comparing across tasks is a bit difficult. This is why there is growing interest in physiological and neurophysiological tools. In our research, we explored two non-invasive techniques: eye tracking and functional near-infrared spectroscopy, or FNIRS. Eye tracking captures eye movements and pupil size, while FNIRS measures changes in brain oxygenation. Both offer real-time insights into how hard someone's brain is working. We paired these tools with machine learning to identify which features best predict cognitive workload levels. Our study combines data from two parallel projects, one using eye tracking, the other using FNIRS, which are both built on the same experimental design and protocol. Before diving into the experimental protocol, it's important to understand the two key technologies being used in this study. First, FNIRS, or functional near-infrared spectroscopy, is a non-invasive brain imaging method that uses near-infrared light to measure changes in blood oxygenation. The system includes light sources and detectors placed on the scalp. Light from the source travels into the brain, and the detectors capture how much light is absorbed. Then, using algorithms, we can calculate oxygenated and deoxygenated hemoglobin levels, which reflect brain activity. These measurements are taken across multiple regions in the brain and can be grouped together for analysis. This study focuses on four brain regions: the left and right anterior, medial, and dorsolateral prefrontal cortex. Next, the eye tracker is another non-invasive tool that uses an infrared LED and a camera to monitor eye behavior. The LED illuminates the eye, and the camera captures in high-speed images of the reflected light in the eye. By analyzing changes across the images, metrics such as eye position, pupil size, and blinking behavior can be extracted. From this, biomarkers that indicate mental effort and changes in cognitive workload can be derived. For the experimental protocol, 35 participants between the ages of 18 and 31 were recruited to complete 8 unmanned aerial systems, or UAS, simulator scenarios. After providing consent, participants were calibrated to both the eye tracking and FNIR systems, followed by a 30-second baseline recording of their biometric data. Participants then completed a series of UAS tasks, which required them to scan a simulated residential area at a controlled altitude and speed along a designated flight path while using joystick monitors to locate targets, specifically a civilian red bus. The scenarios varied by task type and difficulty. There were two types of tasks: a scan task, where participants searched for a single target across 3 areas of interest, and a target find task, where they needed to find one target in each area for a total of 3 targets. Target find tasks were presented under 2 levels of visual difficulty: 0% haze and 95% haze. The 0% haze condition was considered a low workload condition, while the 95% haze was considered a high workload condition. Each participant completed 3 scan tasks, 3 target find tasks at 0% haze, and 2 target find tasks at 95% haze, for a total of 8 scenarios. After each task, participants completed the NASA TLX survey to self-report their perceived workload. Through each task, FNIRS, eye tracking, and behavioral metrics related to their scanning behavior were continuously recorded. For analysis, data from the final 0% haze task was labeled as representing low cognitive workload, and data from the 2 95% haze tasks were represented as high cognitive workload. In this study, a range of metrics were collected to determine which features could best assess cognitive workload. Before we had extracted any biomarkers, both the eye tracking and the FNIRS data were pre-processed to reduce noise and account for any confounding factors. For the eye tracking study, 8 key biomarkers were derived: the number of blinks per minute, the average blink duration, the mean pupil diameter change, the number and duration of fixations, which represents the moments when the eye is still in focus, number of duration saccades, which are the rapid eye movements between fixation points, and the peak saccade velocity, or how fast the eye moves at its fastest point during the task. On the F-near side, the mean oxygenated and deoxygenated hemoglobin concentrations from 4 regions of the brain were calculated. The left and right dorsolateral prefrontal cortex, respectively known as the LDL-PFC and the RDL-PFC, and the left and right anterior medial prefrontal cortex, known as LAMP-PFC and RAMP-PFC. These regions are often involved in decision-making and attention, so changes here can reflect shifts in cognitive workload. We also collected behavioral data, which captured how well participants scanned the required areas. This was measured as scan percentage, or the amount of area scanned within the boundaries of the designated areas of interest, overscan percentage, or the amount of area scanned beyond the boundaries of the designated areas of interest, and not scanned percentage, the amount of area within the boundaries of the designated areas of interest that were not scanned at all. Finally, we gathered subjective data using the NASA TLX survey. This included participant ratings of their mental, physical, and temporal demand, as well as their perceived performance and frustration level after each task. To analyze the features we collected, we took a two-step approach, looking at each feature individually and then in combination with others. For individual analysis, we used linear discriminant analysis, or the LDA model, which evaluates how well a single biomarker can distinguish between low and high workload conditions. For combinations of features, we use the support vector machine, or the SVM model, and the logistic regression, or the LR model, both which are commonly used in cognitive workload studies. To identify the most effective feature sets, we use the sequential forward selection algorithm. This algorithm builds up combinations of features one at a time, aiming to maximize model performance while keeping the feature set as small as possible. We validated our model using a leave one group out cross-validation, which is a method similar to k-fold cross-validation, but is mainly designed for group data. So one participant's data is always being held out during each fold. Finally, we assessed the performance using F1 scores and model accuracy to determine how well each model classified cognitive workload states. First, we analyzed individual biomarkers using the LDA model. Shown here are 8 biomarkers in total. The 2 eye tracking features with the highest F1 scores, the 2 with the lowest, and then the same for the F-nears. This spread highlights which individual metrics were the most and least effective in distinguishing between high and low cognitive workload. The rest of the features fell between these extremes. Afterwards, we tested all available features, behavioral, subjective, and either the eye tracking or F-nears, using the SVM and LR models to establish a baseline. Then, the sequential forward selection algorithm was applied separately to each model to identify the optimal feature combinations that maximize performance. In the eye tracking study, the selection algorithm identified peak saccade velocity, not scan percentage, and participant performance ratings as the best feature set for the SVM model. For the LR model, participant performance ratings were selected alone. In the F-near study, the selection algorithm identified the mean deoxygenated hemoglobin concentration of the LDL-PFC region as the optimal feature for the SVM model. For the LR model, the best performing set included the deoxygenated hemoglobin concentrations from both the LDL-PFC and the LAMP-PFC, as well as scan percentage. When the SVM and logistic regression models were retrained using the selected feature sets, both the F1 scores and accuracy had improved. While both models in both studies had shown better performance, the SVM model with the selected features in the eye tracking study had achieved the highest overall performance, and the LR model with the selected F-nears features showed the highest performance within the F-near study. When analyzing the results, there are 2 key takeaways. First, the F-nears data showed strong performance on its own. This is evident from the selection algorithm consistently identifying the deoxygenated hemoglobin level of the LDL-PFC as an optimal feature for both the SVM and LR models, as well as its own individual strength. This suggests that this F-near marker may serve as a reliable standalone predictor of cognitive workload, and potentially even more powerful when combined with other F-nears features or behavioral metrics. In contrast, for the eye tracking data, peak saccade velocity was actually one of the weaker individual predictors, showing a low F1 and accuracy score. However, it was still selected as part of a feature set that produced the highest model performance overall. This indicates that while eye tracking features alone may not be strong indicators of workload, their predictive power improves significantly when paired with behavioral and subjective measures, suggesting the importance of a multimodal approach. Future research will include how we combine FNIRS and eye tracking together alongside behavioral and subjective data to improve cognitive workload prediction in real-world applications. Thank you so much for taking the time to listen to my presentation. If you have any questions, please feel free to reach out and ask.